They choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Engineering culture, desperately draining the polar to irrigate their cold, dry planet. For the novelist H.G. Wells, this vision of a doomed engineering culture fighting for survival on a ruined planet offered a vivid metaphor of an over-industrialized Victorian Europe rushing headlong towards apocalyptic destruction. The Martians seemed amazingly busy. I began to ask myself, what could they be? Were they intelligent mechanisms? Such a thing, I felt, was impossible. Or did a Martian sit within each, ruling, directing, using, much as a man's brain sits and rules in his body? I began to compare the things to human machines, to ask myself, for the first time in my life, how an ironclad or a steam engine would seem to an intelligent lower animal. It was a walking engine of glittering metal, striding now across the heather, articulate ropes of steel dangling from it, and the clattering tumult of its passage mingling with the riot of the thunder. A century later, the notion of somewhat less advanced life on Mars still persisted. As late as the mid-1960s, NASA even went so far as to offer us a few of the inhabitants that might survive the unbreathable atmosphere and vicious Martian climate. They envisaged creatures, half plant, half animal, with rock-like shells to survive the deadly radiation. They were expected to live off ice locked in the frozen Martian soil and creep about like limpets. But these primitive animations marked the end of an era. By 1967, it was clear there were no Martians. In 1975, NASA launched 2 unmanned spaceships towards Mars. Viking 1 and Viking 2 would actually land on the Red Planet. On arrival, each Viking divided in 2. One part, the orbiter, would send electronic images of the entire planet back to Earth. The other part, a capsule, descended to the surface. Like Earth, Mars has an atmosphere that can be used to slow a descent. A parachute was deployed, removing the heat shield. The lander legs were deployed. Finally, the parachute was discarded and retro rockets fired to make a so-called soft landing at a bone-crushing 10 kilometers an hour. Instruments on board sprang to life, and the antenna unfolded to stare back at a star on the Martian horizon called Earth. This was the first ever color picture from the surface of another planet. The technicians at NASA's Jet Propulsion Laboratory gave it a blue sky. But within hours, they realized that Mars did not have a blue. The red planet had a pink sky. Apart from the startling color, there seemed to be little here. After a century of hope, these rubble-strewn plains of lifeless dust seemed a dreadful disappointment. For safety, both Viking landers were put down on smooth Martian plains. But geologically, the surface of Mars is almost as varied as Earth's. Great volcanic lava flows can be found on Mars. not unlike this one in Arizona, close to where geologist Harold Masursky has spent the past 10 years decoding Viking data from the red planet.
Mars is red because it's rusty, and it's rusty for a very interesting reason. There's lots of water on Mars. High in the atmosphere, it photodissociates into hydrogen and oxygen. The hydrogen escapes because the gravity isn't strong enough to hold it, and the oxygen is combined with the iron in the rocks to make red rocks. So this complicated chemical process results in Mars being remarkably red. And red soils on Earth are very infertile soils because they eat up the carbonaceous material that makes fertile soils. And Mars is unimaginably more hostile than the reddest soil on the Earth. The ultraviolet radiation makes it chemically very active because meteorites come in and break apart and scatter out. And on the moon, we found lots of little fragments of carbonaceous meteorites, but none on Mars. The soil ate them all.
If that sounds alarming, it is. There is great concern about the damage Mars could inflict on Earthlings. Apart from deadly ultraviolet radiation and soil that devours organic material, Mars has a hostile climate. Geologist with the U.S. Geological Survey, Michael Carr.
It's extremely cold. The warmest places are about the same temperature as the coldest places on the Earth, about the temperature of Antarctica. And when you go to the poles, the temperatures are the temperature of dry ice, extremely cold. The atmosphere is quite thin. It's about 1/100th of the Earth's atmosphere, and it's made of carbon dioxide. It's not oxygen, nitrogen like the Earth's. And again, the winds vary with the season. For most of the time, they're really quite calm winds. You wouldn't feel buffeted by them. Look at some of the pictures that we took from the Viking orbiters. You can see the fronts, and they look like the weather systems we see on TV. You can see nice spiral fronts, and they moved westward just like they do here on Earth. And there are storm systems at certain latitude bands. There's a lot of weather. And of course we have snow. It's carbon dioxide snow there, but the ground gets covered with snow in winter and so forth. All of us are interested in how life started, and the record here on Earth has been destroyed. There really is no record of the gap between non-life and life. It's destroyed, and there's a speculation as to whether it was an inevitable evolutionary process here on Earth, or whether it was due to some very low probability events and so on. Go to Mars and look at the early history of Mars and see if life got going there too, then we'd have a much better understanding of how it happened here on Earth.
While most scientists now accept that there is no life on Mars, there is disagreement about whether life might have existed once. Part of the speculation centers on pictures like these. Taken from the orbiting half of the Viking spacecraft, in the same way as that remote satellite view of Los Angeles, these images offer a tantalizing prospect of a very different Mars from the one we know. This is an area known as East Mangala Valles. The picture is dominated by a huge impact crater. The splash-like ejector blankets thrown out by the impact have covered part of what looks unmistakably like an outflow delta. The evidence for some kind of flowing material is even greater when we look at the canyons carved through the surface rock. On Earth, only water or glaciers do this.
There is abundant evidence from the surface that liquid water has been present there, particularly very early in Mars's history. It appears that water frequently and commonly flowed across the surface. And if that was so, it has implications about the temperature-pressure conditions. And so the atmospheric conditions may have been quite different very early. Now, we don't know what that implies as to whether there would be a protective ozone layer like there is on Earth, whether that would have formed too. There's too many uncertainties. But one thing that is, I think, certain, that the climatic conditions and the atmospheric conditions early on in Mars are quite different from what they are today.
The impact crater ejector blanket looks like a thick, muddy splash. Geologists believe evidence of ice and subsurface permafrost melted at the moment of impact, pouring back over the dry, frozen river delta. Two things seem clear. If water did flow on Mars, it seems to have flowed and then frozen before the major impacts from asteroids occurred. Did the impacting asteroids finally destroy any protective atmospheric blanket Mars might have had, causing liquid water to vanish or even freeze under the soil? And more important, did life get started in the water before all this happened? From NASA's Ames Research Center, Dr. Carol Stoker.
If we understand evolved on Earth, then it's almost inevitable that life should have evolved on Mars at pretty much the same time, because at the beginning of the planet's history, Mars and Earth were very similar. And for the first 500 million years to a billion years, Mars and Earth were virtually indistinguishable. And we know that by 500 million years after the planet was formed, Earth was covered with life. We have plenty of fossil evidence for that. And if our understanding of how that life got there, you know, unless it was divine intervention or panspermia or something, there should very well have been life on Mars at the same time.
Within all living things is another microscopic universe of molecules called proteins and nucleic acids. This famous double helix of deoxyribonucleic acid, or DNA, plays the genetic role. It has been likened to a code that replicates itself, but which can also take advantage of useful changes or mutate. Biologist Dr. Norman Horowitz.
The property of mutability, or mutation, is what distinguishes living things from things that mimic life in one way or another, but are not, in fact, alive. A flame is a good example. A flame shows metabolism. It can reproduce by means of sparks. It moves around, but it can't mutate, and so it's not alive, except perhaps in a poetic sense.
This rather unpoetic organism is what we will look for when we go to Mars. Called a filamentous cyanobacterium, it is one of the earliest known fossils found on Earth. In less than 20 years, we have come from expectations of shelled creatures scuttling across the Martian plains to single-celled fossils that might have lived in a slimy corner on this planet more than 5 billion years ago.
Life is life. I mean, even if it's microscopic, it has the potentiality to become as large and as complex and as intelligent as we are, if those words apply to us. It's life, and that's the important thing. If we can be sure that we've identified living matter on Mars, even if it's very simple, that's a great discovery. And even if it doesn't exist anymore, if it existed at one time, that would be important.
It has been speculated that primitive life might still exist in the permafrost known to be the surface of Mars. That perhaps even now, beneath the feet of the inert Viking landers, single-celled organisms are hanging on in a last desperate effort to survive. A sort of microscopic version of those tenacious canal-building Martians that Vikings' robot arms simply couldn't dig deep enough to find when it scratched a sample of red dust from the frozen surface.
In order to have life on a planet, you've got to have energy. Has to reach that life. And you cannot sustain a living population beneath the surface of a planet. Even if there were water, let's say, at some depth beneath the surface of Mars, you couldn't maintain a living population there very long unless it has access to the sunlight. Ultimately, the sun is a source of energy for life on our planet, and doubtless that would be true on Mars as well. From the point of view of an observer on another planet looking at our Earth, the Earth must be a most unique and unusual wet place. Such an observer would find it hard to believe, I think, that 20% of the Earth's surface is covered with deserts where water limits the abundance of life. And yet there's enough water in our oceans to cover the whole surface of the Earth to a depth of something like 2 miles if it were all spread out. This shows how important liquid water is for life on our planet. And it helps explain why the Earth is such a unique place. We have liquid water.
What has happened to the atmosphere of Mars is it has turned into carbonate rocks, most likely. And the reason this didn't happen on the Earth is that we have plate tectonics, so that the carbonate rocks are subducted into the interior of the Earth and then re-outgassed in the form of carbon dioxide, and it keeps the cycle going. There is also probably an initial complement of volatile gases on Earth that was larger than on Mars. So the Earth also had a primarily nitrogen atmosphere after the carbon got sucked off one way or another. On Mars is too small for plate tectonics to occur. And so once the carbonate rocks were formed, that was it. And as soon as the atmospheric pressure dropped below what's called the triple point of water, and the triple point is the point at which liquid water can no longer occur. A stable liquid phase for water is not allowed. And it's just a very funny coincidence that the atmospheric pressure on Mars is at precisely the triple point of water. So once the atmospheric pressure drops below the triple point of water, you can no longer form carbonate rocks, and the process stops. But then you no longer have liquid water. And every terrestrial organism, at least, needs to have liquid water to survive. And liquid water is just a sine qua non for biology. So it's very easy to believe that once that happened on Mars, once there was no longer enough atmospheric pressure to support liquid water, life was wiped out.
A dry, cold, toxic world, and yet more Earth-like than anywhere else in the solar system. Now, as we approach the 21st century, our technology has only just reached the point where we can realistically plan a human mission to this strange place. But before then, another high-resolution orbiter will be dispatched, because despite the apparent detail of these Viking images, there's much we cannot see. When Viking 1 sent its first black and white pictures to Earth, scientists who thought they'd chosen a smooth landing site were shocked to see how closely it had missed wrecking itself on a large boulder just 9 meters away. The size of a small family car, it was nicknamed Big Joe. Objects much bigger than Big Joe had been completely invisible to the cameras on the Mariner satellites that surveyed the surface of Mars in preparation for these Viking landings. At the U.S. Geological Survey, geologist and imaging specialist Alfred McEwen.
We get here the raw data that comes from the Jet Propulsion Lab, which is in image format already, but it contains the electronic noise and camera distortions in the data, and there are many separate frames. What I've produced here is a mosaic composed of 102 Viking orbiter frames, and it's much easier to look at one picture where all of these pictures have been cleaned up and put together rather than try to look at a pile of 102 individual images. This image has a resolution of about 800 meters, or say a football field, so we couldn't see something the size of trucks, for example.
The reason for this are the picture cells, or pixels, that these images are built from. If something the size of a truck can be lost within a single pixel, sending a spaceship to anywhere other than a smooth plane will be too dangerous. So orbiters with cameras capable of detecting rocks smaller than Big Joe will visit Mars in 1992. Because the scientists want to go to places like this, Olympus Mons. A vast volcano, it is 28 kilometers high. Its base would cover the state of Arizona. Using the same processors that achieved that synthetic flight over Los Angeles, technicians at the Jet Propulsion Laboratory can now fly over one of the greatest geological features in our solar system. But geological sightseeing and the search for fossils is only part of the story. Some scientists at NASA have plans to live on Mars.
Mars is a sort of St. Louis of space. It is the gateway to the outer solar system.
At its closest, Mars is about 55 million kilometers from Earth. It makes no sense to attempt the year-long journey in one jump. At the moment, plans for a human mission are far from fixed. But by assembling known technologies, we can build a fairly accurate picture of how it will have to be done. First, hundreds of tons of building material will be lifted 400 kilometers into Earth orbit. For this, multiple shuttle launches will thunder away from the Florida coastline to an eerie, weightless building site. This is the latest NASA computer simulation of how it will work. Using robots and spacesuited astronauts, an improbable web of girders, rods, and empty fuel tanks will be locked together to build a huge pier in space. Until the Challenge temporarily halted missions, most of the techniques for this orbiting assembly had been rehearsed and proved feasible during exercises within the shuttle cargo bays. Power for the space station will be captured from the sun using extendable solar panels. Plans for this stage of the mission to Mars are already well developed. Program Manager for Long-Range Planning, Jesco von Puttkamer.
We will be launching the space station in 1994. It'll be occupied 1995, and then it'll undergo growth phases, and probably will grow all the time into the early years of the 2000 and beyond. So there's nothing finite about the space station. It's a capability rather than a piece of aluminum or like a lunar landing, a goal which you can reach. Once it's there, and there's no turning back then. It's irreversible.
The space will be a workshop. The components for the Mars spacecraft will be assembled here in orbit. But already the price of the project is a cause for concern.
So by the year 2010, we ought to be ready to go to Mars. The cost of getting there is incredibly much higher than really what we had to spend for the Apollo program. It's between $50 and $100 billion. It will require, in my opinion, the participation of several nations, spacefaring nations. If you do it as a crash program for national reasons, like beating someone else or for patriotism, I don't think it's going to get done.
The Mars spacecraft will be launched from the orbiting space station. The actual crew compartment, no bigger than a small caravan, will be almost obscured by fuel tanks, space debris shields, and communication dishes. Once outside the gravitational influence of Earth, 3 spacecraft will join together. Then, using the gravitational forces of the solar system like a slingshot, they will drift for a year, like some vast spore of pollen, through the blackness of space at thousands of miles an hour, until they are pulled towards Mars. Director of Advanced Projects for Exploration of the Solar System.
When we got to Mars, first of all, we would do something slightly different. We would have it wrapped in what we call an aero capture sheath. The universe has been designed with planets with atmospheres. Atmospheres are great places to dissipate heat and energy. You don't need a rocket to fire huge retro maneuvers to go into orbit around another place. If you're clever, you can dig down into the atmosphere, absorb the heat on this sheath, and then end up in orbit around the planet. It's a very efficient way to do things. Then eventually, we would then separate a capsule from a mother craft, which would stay in Martian orbit, and it would go down on the surface of Mars.
Landing vehicles will have to be of 2 varieties, one which is returnable, which brings a crew back to Earth, and the other which is non-returnable, is sort of a cargo vehicle, since you'll need a lot of cargo, especially for initial missions. And to just simply use those cargo vehicles as habitats for the first few missions. But because of the very severe radiation environment on the surface of Mars, there are no Van Allen belts. Those radiations will be very destructive. So to protect them from that, you want to cover them with about 1 meter of soil. So one way you could do that is to simply scrape, using a drag line, scrape soil over a shell from a cargo vehicle. Probably the most economical and safest way to put a base on Mars is to use Martian resources to the fullest extent possible. So that way, 2 things it gets you. One is that you don't have to bring things from Earth. You don't have to go to the expense and the long waiting period to bring those kinds of resources from Earth. And the other is that there's a safety factor. There's a built-in safety factor by virtue of the fact that if the supply ship doesn't arrive, you don't die. Food could be grown in greenhouses that would be enclosed. Those greenhouses could either be above ground in a sort of a plastic bag configuration. Food crop type plants can grow in fairly low pressures, 200 millibars, 100 millibar type pressures, and primarily CO2. So 100 millibars is about what a child's balloon, about the pressure that it is above the ambient pressure of the atmosphere, so that it only takes a very thin sheet of plastic to maintain 100 millibars pressure on the surface of Mars.
In the Arizona desert, a small group of researchers claim to have developed a greenhouse habitat suitable for transfer to Mars. They grow plants under controlled conditions. The biological essentials of sunlight and liquid water are combined with nutrients to produce healthy, edible food crops. The soil, sterile gravel, is nothing like as hostile as Martian dust. Although by adding nutrients through pipes directly to the plant's roots, the researchers believe they could grow vegetables on Mars. These greenhouses are not sealed against the climate. They don't need to be, but on Mars they would. So this privately funded team have built a sealed glass and steel box. They call it Biosphere 2, acknowledging Earth as Biosphere 1. Inside this damp, hot, regulated microclimate, even the sunlight is computer controlled, along with the atmospheric pressure and the sanitized water. The claim is that if humans have to spend months on Mars, they will need an Earth-like environment to live in.
It looks very strange.
Is it on the lettuce itself?
No, it's just on the roots.
If this group of researchers is correct, then growing crops, tending fish, laced with a sprinkling of Eastern mysticism, will help form the essential ingredients for a healthy life on Mars. A view not shared by everyone. Michael Carr.
Now, I see all these fancy pictures of huge greenhouses and, you know, forests growing in them and good and lily ponds and so forth. And I have some trouble believing that that's going to be there on Mars. I really do. And I have some trouble understanding what the purpose would be. Why would you want to do that? Why would you want to make this incredible investment in setting up something like that?
The thing we would do, which would be the greatest engineering achievement for humanity, would be to terraform Mars. Now, what do we mean by that? That would be to make Mars into a place that human beings could live. Now, there's quite a few doomsayers out there who would say, oh my gosh, we're going to export the lessons that we've learned on how to ruin this planet to another one. But I'm optimistic. I think that by the time you would spend all the time and effort to construct another planet as a place for human beings to live, that you would have learned how to invoke the mechanisms to make it be a good place to live. But that's distant. That may be 150 years, maybe 200 years.
Terraforming generally has implications of changing the environment of the planet itself. Now you can have local hospitable environments, I think, that you could set up, but I doubt that you can change the planet. Planets are very robust things, very resistant to change.
You can become independent from Earth on Mars. Every resource that's needed to sustain life is on Mars, and with a little technology and a little bootstrapping to get yourself started, you can certainly become completely self-sufficient from Earth on Mars.
The main function of man in space is entertainment, actually. I think that instruments can do better than man under most circumstances when you talk about space and planetary environments.
The great thing about doing a biological ecosystem research in space is not just that you are able to develop optimized biospheres in space for humans eventually, which will serve us better eventually than the Earth's biosphere will, which is not optimized for humans. But we will also learn about biospherics in space in order to be able to come back to Earth and protect and develop and maintain our own biosphere down here on Earth.
Before the first humans step onto the surface of the Red Planet, a series of robot voyages are planned. Unlike Viking, these will rove across the Martian landscape, picking up samples, analyzing the atmosphere, and continue the search for fossil evidence of life. Rovers are not new. This one, built in 1963 for the moon landings, was to be radio-controlled from Earth. On Mars, this isn't possible. It takes at least 20 minutes for a signal to get there, by which time the rover might have wandered over the edge of a canyon or jammed in rocks. A rover like this would need to be autonomous, only contacting Earth when it was unsure of itself. So the first task is to give it stereo vision. Supervisor of the Robotics Research Group at the Jet Propulsion Laboratory, Brian Wilcox.
What I have here is two video monitors, one above and one to the rear, which are combined by a half-silvered mirror at 45 degrees and are polarized so that when I wear polarized glasses, I can see the image in 3 dimensions. The image that I have presented there is a stored image of our test course that we use this vehicle with, and it allows us to test the control concepts that we'll use on Mars. The particular control concept that I have shown here is to use a joystick to move a cursor around in the display. I can designate a point to there and then free up the cursor for a succeeding point, for example, designate that point, move to this location, so I can have the vehicle execute that path. If I were in very rough terrain, I would have to do that from Earth because we wouldn't necessarily have enough confidence in the onboard software to maneuver through extremely rugged terrain all by itself.
Now fitted with 2 widely spaced cameras as eyes, the old lunar rover has been dusted off and rewired with a modern onboard computer. It will follow Wilcox's predetermined route or find its own route by comparing what it sees with mathematical maps stored within its memory. So contact with Earth can be kept to a minimum. With intelligent, agile vehicles like this, NASA hopes to gather more crucial information about the Martian surface.
Even the Viking mission of 1976 told us that the soil is very unusual, and in fact it's so-called superoxidating. That means that it reacts very violently with some kinds of materials, which might include plastics or rubbers that could be used on spacesuits and things like that. So it would be very important, of course, not to find that we had designed spacesuits and we get to Mars and find out that the soil reacts violently with the materials in the spacesuits. So that much we know already, although we don't know the details of that chemistry. We do know that there's something to watch out for there. Furthermore, a rover might find water under the surface of Mars, frozen water in the form of ice, which would allow us to plan a mission around that. If the mission were an extended one, where we wanted humans to spend a year or more on the surface of Mars, the life support equipment for that, if we had to bring everything, including all the water and all the oxygen and so on from Earth, would be very expensive. It would be much less expensive if we were to know in advance that there was water on the surface and to know that we could perhaps recover oxygen in a simple way from the soil.
Here at the University of Arizona, another autonomous rover project is underway, which takes a completely different approach to the difficulties of moving over the surface of Mars. Buck James is student administrator at the Department of Space Sciences, where, using components from the local hardware store, they've built this unlikely prototype machine, the Mars Ball.
The Mars Ball is a different concept in Martian rovers, working basically on compressed air. It's composed mainly of these two large wheels, which have these large airbags on their outside, which can be inflated or deflated under computer control. The air to fill them is just atmospheric air, which is sent into a central hub within the wheel by these typical compressors. They're basically just vacuum cleaner compressors, which take the air from the outside and send it inside. The wheels are then connected to a central payload, which would house the scientific instruments and currently houses the onboard computer, which controls the valving. The computers talk to each other. There's a computer in each hub, as well as the computer in the payload, talk to each other through these slip rings, which allows the electrical connection even though the wheels are turning. Now, in actual use, it would set down on the ground like this for testing of the Martian soil. And if you follow me around the outside, we'll see the valving, which actually controls the airflow into the bags, is very simple. The valves only have two positions. The bags are either being inflated from the central hub or they're being deflated to the atmosphere. We're currently operating, obviously, with Earth atmospheric pressure, which is considerably higher than Martian pressure. However, even on Mars, the atmosphere should be sufficient that with a more efficient blower system, as I get pushed out of the way here, the system should be able to work.
The atmospheric pressure on Mars is about 1/100th that of Earth, so the Mars Ball compressors would have to be very efficient. Designed to travel at 1 kilometer a day, the main advantage of the Mars Ball is its capability to absorb rough terrain that might halt other small wheel designs. While possessing nothing as sophisticated as stereo vision, it is designed to travel without the need for human intervention.
To control it from Earth would require constant use of the deep space network, and you simply could not afford to tie that up for a year. So this machine is built to operate for several hours at a time, simply rolling over anything that gets in its way. The machine is designed to be so cheap and easy to that it might, in fact, be easier to set two of these down than one more expensive, more intricate machine which is capable of moving faster. So slowness is not really a design flaw in the thing. It was built to do that.
On Lake Mirage in California. The temperature is just above freezing.
Looks as if we're in pretty good shape, Tom.
For Jim Burke, an engineer from the Jet Propulsion Laboratory, the conditions are ideal for possibly the most bizarre Mars rover idea of all.
I think what we're going to want to do is to take one of them out and put it together, leaving the other one safely tied in here. Now, I've got this one ballasted to what I think is about the right amount. Let's let it
He plans to fly balloons on Mars.
These are a convenient toy with which to learn some things about how the big balloons will behave, and it may look like just playing around, but in fact, one can learn quite a bit with these. Our helium balloon has got more lift this morning. All right, now if you let me have it just for a moment, I'll let it just go.
The idea is brilliant in its simplicity. Red helium balloon holds up the black hot air balloon, which inflates when warmed by the rising sun.
Okay, let's connect up our drag rope and simulate a Martian takeoff.
The hollow drag rope will contain the sampling devices for gathering information, pulled over the surface by balloons carried on the Martian breeze.
So this presents the opportunity of doing both detailed surface measurements during the time when the rope is on the ground, and overhead measurements such as with a little camera when it's traveling along during the day.
Burke is not playing. Everything is recorded, including the solar temperature.
Now the solar balloon is inflating over there, and if you leave it right now, Tom, I'll bet you that it'll just sit here for a while. It may inflate, it may go up, it may not, but we'll watch it. Obviously, in this model, the drag rope has far more drag relative to the balloons than it would on a real Martian system, which is why we're pulling on it a little bit here to relieve it. But you see the balloon is already starting to lift, so pretty soon it will start to drag the rope. Eventually, well, it's 2 minutes and 17 seconds now, we may eventually see it develop enough lift that it will actually pick up some of the rope. There she comes. How's that for a forecast? Right now we're having an excellent simulation of a Martian morning takeoff. Of course, we may see it go completely away, but if so, that'll mean I haven't provided enough rope. I guess we will have to grab it if it actually goes up. Let's see, we've got 2 minutes, and we've got 4 minutes now. We are at the bottom of a deep, dense ocean of air here. The Martian atmosphere is as dense as Earth's atmosphere, 30 kilometers up.
In the end, perhaps Mars will provide an opportunity to reassess our attitudes, not just to technology, but if evidence of life is found, to ourselves. As Gentry Lee said, to see how we fit in the larger puzzle of things. Following these first bleak pictures from Viking, science writer Jonathan Eberhart was moved to write a song about Mars and the Earth-like atmosphere it lost more than 5 billion years ago.
Times 100,000 dusty years ago, where now extends the plain of gold, did once my river flow. It stroked the stones and spoke in tongues and splashed against my face. Till ages rolled, the sun shone cold on this unholy place. So many stars bedeck my skies when once there were but few. But oh, to know again the clouds that hid them from my view. My ochred cliffs and rusted sands stand regal and serene. But oh, my wan and wasted world, I miss your blue and green. But it's just the weight of waiting, not a death watch or a friend. Tomorrow has a starting, as does yesterday an end. for the water of my river and the air that was my wind. Though bound in rocks and wintry wastes, I pray may flow again. My ochred cliffs and rusted sands stand regal and serene, but all my wan and wasted world, I miss your blue and green.
As an entire species, we need a peaceful technological activity that is on point and represents the summing up of our collective curiosity. What better way than to go to Mars and learn about another world?
If we as Americans or we as the free world don't do it, the Soviet Union has made very clear its plans to do it. If neither we or they do it, someone else will. And it will certainly happen within the next 50 years because it is so eminently possible to do it.